We have learned that devices within a network communicate with each other. How does a device determine if another device is part of the same network? That's where subnet masks come into the picture, helping devices identify network boundaries. A subnet mask is represented in the same format as an IP address, and its binary format must consist of all ones followed by zeros. Let's take a closer look at how subnet masks work with IP addresses. Here's an example where the IP address is 10.0.0.4 and the subnet mask is 255.255.255.0. In this scenario, the subnet mask reveals that the first three sets of numbers, 10.0.0, denote the network, while the last number, .4, identifies the host within that network. You might be wondering, how do we deduce this? The answer lies in the binary form of the subnet mask. When we convert the subnet mask 255.255.255.0 to binary, we see a continuous string of ones. This string designates the network segment, while the zeros indicate the host portion of the IP address. This information informs the device that if another device's IP address also starts with 10.0.0, then that device is part of the same network. Furthermore, the subnet mask is not only used to determine whether a device is on the same network, but also to calculate the number of possible hosts in that network. In our example, the subnet mask 255.255.255.0 has 8 zeros in its binary representation. The number of hosts can be calculated using the formula 2 to the power n minus 2, where n is the number of zeros. So, the network 10.0.0.0 with the subnet mask 255.255.255.0 can have 2 to the power 8 minus 2, which is equal to 254 hosts. This implies that you can have up to 254 devices, each with its own unique IP address, ranging from 10.0.0.1 to 10.0.0.254. You might be wondering, why do we subtract 2? Well, within any network, the first address is reserved to represent the network itself, in this case, 10.0.0.0. Additionally, the last address is designated for broadcasting messages to all devices within the network, which here would be 10.0.0.255. Consequently, these two addresses cannot be assigned to individual devices. Therefore, we subtract 2 from the total. Let's examine another example, where the IP address is 192.168.1.2, and the subnet mask is 255.255.0.0. In this case, the subnet mask indicates that 192.168 is the network portion and .1.2 is the host portion. Since the binary representation of this subnet mask contains 16 zeros, we can calculate the number of possible hosts in this network. As we discussed earlier, we use the formula 2 to the power of n minus 2 to do this, where n is the number of zeros in the subnet mask. In this instance, that gives us 2 to the power of 16 minus 2, which equals 65,534 possible hosts. This means we can assign IP addresses ranging from 192.168.0.1 to 192.168.255.254 to devices within this network. Remember, the first address 192.168.0.0 is reserved to identify the network itself, and the last address 192.168.255.255 is used for broadcasting messages to all devices in the network. These two addresses are not available for individual device assignment. Subnet mask can also be represented in another way using classless interdomain routing or the CIDR notation. In CIDR notation, the subnet mask is expressed as a slash following the IP address, then a number which represents the count of consecutive 1 bits in the subnet mask. So, instead of saying our subnet mask is 255.255.255.0, we could say it is /24. This is because 255.255.255.0, when converted into binary, has 24 bits set to 1. When we consider an IP address such as 192.168.1.5 with a subnet mask of 255.255.255.0, it would be written as 192.168.1.5/24 in CIDR notation. The /24 signifies that the first 24 bits of the IP address are used for network identification, while the remaining bits are used for host identification within the network. You can view your subnet mask by using the ipconfig command on the Windows command prompt. and ifconfig on Mac and Linux terminals. Alright folks, that's it for our explanation of subnet masks. We've seen how these critical components of network communication help devices determine if another device is on the same network. We've learned how the subnet mask is used to calculate the number of possible hosts within a network. We have also gained insights into CIDR notation, which provides an alternative way to represent subnet masks. If you found this video helpful, don't forget to hit the like button, share it with your friends, and subscribe to our channel for more informative content like this. Thank you for watching, and I'll see you in the next video.